Hi, so today we're going to talk about Maxwell-Stefan equation and how it expressed as difference in component velocity is equivalent to the Maxwell-Stefan equations expressed in terms of molar fluxes and molar diffusive fluxes. So we're going to write out first the Maxwell-Stefan equation, okay? So um, equation is equal to the driving force equal to the sum where I is not equal to J times Xi times Xj, so like molar fraction of I and molar fraction of species J. So I and J are different species or different states. Over to the diffusion coefficient of I and J times the velocity difference between I and J and I. So so for total flux of a species, we would have n molar flux of that species is equal to the concentration times the mole fraction of that species times um the velocity of that species. So we have the molar flux of species I equal to concentration times its molar fraction times its velocity. So then we would have VI is equal to its molar flux over the concentration times mole fraction of Xi, mole fraction of I. So then we would have, so the same thing apply for J. So Vj would be Nj over Cxj. All right, so for the unit of flux, we would have uh Ni is equal to concentration is mole over volume times mole fraction doesn't have a unit, and then VI would be meter per second square or meter per second. My bad. So we'd have mole over meter square times second. So that's the unit of molar flux. So like, oh, it's similar to heat flux. So like over the amount of joule over certain area with over time. So we substitute back to this equation. So we have driving force is equal to some where I is equal to J times Xi Xj over Dij. And then we would have substitute from over here or sorry, J, I mean Nj, C mole fraction of J minus flux of I, concentration minus mole fraction of I. So that's for the total flux equation. So for diffusive flux equation, we have Ni is equal to Ji plus um mole fraction of I times N. So N is the total volume. This equation, we know that Ni is equal to C um concentration times Xi times Vi. And then we have J over I plus Xi, and then we have N. We know N is equal to um concentration of mole fraction of I times velocity, total velocity. So we would have, oh, and then when the total molar, the mole fraction of I would be 1 for pure component. So we would have CXI VI minus CXI V equal to JI, and then we would have um V we would have CXI over Vi minus V equal to Ji. And then so we would have Vi is equal to Ji times Cxi plus V. So, and then since for VJs, let's put V over here. So it'd be J plus CX, mole fraction of species J. Then now we plug it back into our equation. We would have the driving force is equal to some where I is not equal to J times Xi Xj over the diffusion coefficient of both species over Vi is V plus Ji Cxi minus V plus J plus Cxj. So we can get rid of V. So then we would have um I'm sorry, I think I made a mistake over here. So this one should be um Vi should be equal to Ji over Cxi plus V. And same for here. I'm sorry about that. So then this one would be, and then this one would be Cxj. Yep. And then we simplify our equation. We would have Ji Cx more fraction of I minus Jj or diffusive flux of species J's over concentration times mole fraction of species J. So that's for the first question, express the Maxwell-Stefan equation in terms of molar fluxes and molar diffusive fluxes. And then for the second one, we have our chemical potential at pure state. So driving force, diffusion in terms of chemical potential would be written as UI with TPX. So temperature, pressure, and mole fractions is all equal to UI at pure state, and with constant T and constant P. So temperature and pressure are constant here, and then times R T ln X Y I of species I. So now from the previous Maxwell potential equation, we have and our driving force is written in this formula. So D driving force is equal to derivative of UI over um derivative of with respect to Z d dz of UI over RT. And then there's also XI over here as well. So now we're gonna find the derivative of UI, okay? So derivative of UI is just derivative with respect to Z of UI TP at pure state plus RT to the ln XI. So we know that this one is a constant, so derivative would be 0. And then we also have RT is a constant. However, we know that mole fraction changes as Z changes. So we have RT over derivative dz of ln xi. And that would be equal to d over dz ui. So when we plug it back into our equation, d over xi d dz, so derivative ui is just RT because RT over here is already a constant, so it would be RT d dz ln xi times 1 over RT. So we cross cancel this out. We would have driving forces is xi over dz ln xi. And we know that ln xi changes derivative of xy with respect to z is, let's see, 1 over xi times xi. So xi times 1 over xi with d xi, the derivative of the change of xi with respect to z. So now z is canceled out. So now the driving force is only dxi over dz. So that's the simplification. Okay. And then for the third one, we need to show how the Maxwell-Stefan equation and simplify to Fick's law for an ideal binary mixture. So go back to our Maxwell-Stefan equation. We have concentration times distance, or let's go over here. Um, let's just use this equation for now. Let's copy this. And then we can just get rid of this. And then we can move stuff over. So we move a concentration of out and then move it to the other side. So we have CD over XI XJ over concentration of diffusion coefficient of both species over JI minus JJ over mole fraction of I over mole fraction of J. So we know that JJ is equal to JI. JJ plus JI, my bad, is equal to 0. So JJ, JI is equal to negative JJ, or JJ is negative JI. So we would have CD over XI, XJ over DIJ times negative JI XJ minus JI plus I over X mole fraction of I. And then so we take JI out of the bracket. So we would have, so for this equation, let's solve this. Okay, so let's put the negative sign outside. J X minus. So this one we would have the answer would be negative, or negative xi xj over di diffusion coefficient of both substance times ji over 1 times xj xi times each other. Now we cancel this out, and then so we have the negative sign over here and dij and then cd, and then we move the sign over here, and then we rearrange the equation. We would have ji is equal to negative cd um times cd diffusion coefficient of ij times d driving force. And we know that driving force is equal to dx1 over dz that we derived before. And when we plug it in, we have the Fick's law equation, right? And then, so what's the relevance and application of Maxwell-Stefan equation? So it helps. So for problem in class like uh column distillation, where there's a boundary between liquid and vapor, and we want to find the solve for diff diffusion cross diffusion for diffusion problem for both states or multiple substance or species, like this one where there are two different states. Maxwell Stefan equation apply very well. Or in the problem where there are two species, like water that we did before, there's water and then there's nitrogen, while the Fick's law only allow one species. Maxwell can help solving multi-species diffusion problem. All right. Thank you for listening.